Hey everybody, Dr. Briggs here. Today we're going to talk about a problem inherent to partial eta squared. I'll also show you what the solution is, and then I'll walk you through an example of how to actually calculate it. For context here, of course, we're talking about an instance where you would want to calculate a partial measure of effect size. That's usually a within subjects ANOVA, for example, but it's some other general linear models. So there are, of course, other measures of effect size, for example, partial epsilon squared, partial omega squared. Those are perfectly reasonable measures of effect size. However, many people still report partial eta squared. However, it's been demonstrated that it is a biased measure of effect size. For example, Richardson demonstrated that it is biased. It tends to overestimate the size of the effect. In fact, Okada did a very nice demonstration of this, demonstrating that it is always biased. The size of the bias does tend to get less as you have an increased sample size. However, it is always biased, even with a completely null, a completely true null hypothesis. Uh, Partial eta squared tends to be larger than zero, and of course that shouldn't make any sense. So of course now we need to do something with that. Nothing I'm going to talk about here is my idea. I want to make that absolutely clear. Mostly what I'm going to be doing here is demonstrating Mordkoff's method. So Mordkoff has a couple of recommendations here. First of all, he recommends just don't use partial eta squared. Instead, report one of the other measures of effect size, as they tend to be much less biased or not really have any problems. Um, but if you do insist on using partial eta squared, or you find a paper that reports partial eta squared and you want to remove the bias, there's probably enough information in the paper to calculate what he refers to as adjusted partial eta squared. And so he gives a simple method of how to calculate that. And this is what we're going to demonstrate here, what I'm going to talk you through right here. To find adjusted partial eta squared, we're going to need to do a little bit of math. It's not anything difficult. So first of all, as you can see, we're going to have to find partial eta squared and remove it from 1, for example. We're going to subtract that thing from this, and of course, do a little bit of math here. But it's nothing we can't handle, so let's go ahead and start working on that. So naturally, I'm assuming here that you kind of already know how to find some of this information from a publication or in your own statistical work that you're doing. But we'll walk you through that in an example here in just a moment. So as I said, you need to find partial eta squared first, and then you can find adjusted partial eta squared. And so, of course, first we need to calculate the partial eta squared. This is, of course, the equation that you can find anywhere on Google or whatever. So as you can see, we first need the sums of squares from the between groups variance. Then we divide that by the total sums of squares, or the sums of squares from the total variance, minus the sums of squares from the between participants variance. And of course, again, we're talking about a within subjects ANOVA design in this particular instance. So why don't we use a example? Okay, so let's imagine that we have this source table, and this is all of our information from our data. We calculated an ANOVA, and we came up with all of these sources of the variance, as you can see. Now, these are made-up data, although the math will certainly work out in the table. Don't worry about that. And in fact, the scenario doesn't really matter for our purposes. So imagine that we have this source table, and we can calculate partial eta squared from that. Obviously, we simply need the sums of squares from the between groups variance. That's very easy to find here. All of the sums of squares are found in this column, and we're specifically looking for the between groups variance. In this case, we have 143.59. That, of course, becomes the numerator. Now, we need these sums of squares for the total variance, which is right there. Sums of squares, total variance. 1,217.96 we put right there. The last thing we need is the sums of squares from the between participants variation, which is right here, 986.63. So plug all that in. Actually, the math from here is pretty straightforward. So we simply make the subtraction down in the denominator to find a difference of 231.33. Then we divide the numerator by the denominator to get a difference or a proportion of 0.62. Okay, so our partial eta squared, the original measure of effect size that most people are probably reporting, is 0.62. Now, as we've seen, however, that is biased, or as many people have claimed. If you want to know why that works out, you can read their papers. The references, of course, will be in the description of the video below. But of course, now that we have that partial eta squared, we can now find the adjusted partial eta squared, which removes the bias. So that's simple to do. Here again is the equation. So as you can see, all we're doing is taking the partial eta squared we just calculated, 0.62. We're plugging it into there and there, those two places. Now we also need to input another couple of items from our source table. So of course we see the degrees of freedom from the between groups variance, which is right here. DF is all in this column, degrees of freedom, and between groups is 2, so that's going to be a value of 2. And of course the within groups variance, which is right here, degrees of freedom for that is 14. So of course it simply looks like this. We plug in our 0.62 partial eta squared that we just calculated there and there, and 2 goes there, 14 goes there, and so therefore this is it. Now we simply do the math. So we can start simplifying easily. Obviously 2 divided by 14 is 0.14. 1 minus 0.62 is 0.38. Of course, you do what's in the parentheses first as the order of operations dictates. Now, at this point, some people can make some mistakes here. Obviously, we do not subtract 0.38 from 0.62 first. The order of operations dictates that we multiply first before subtraction. So, of course, 0.14 times 0.38 rounded is 0.05. Now we can take 0.05 from 0.62 to find a adjusted partial eta squared of 0.57. So as you can see, it is smaller than 0.62. The adjusted version is smaller. And in fact, if you were to do the partial omega squared from the same information, you should find it at 0.55. So again, you'll see that the adjusted partial eta squared is much closer to the adjusted omega squared. Now, the reason we get slight differences is because we use different figures, different criteria, different characteristics from the data to find our measures of effect size. But as you can see, we've reduced the number, reduced the bias here. And again, this is not my idea. This all comes from Mordkoff. So once again, as we see, partial eta squared is a biased estimator. It tends to be too large. And so we can bring it closer to the, the correct, what is probably the correct effect size by using Mordkoff's method, of course, which is brilliant, very good, and pretty straightforward to do, easy. Now, you may still prefer to report one of the other measures of effect size. The interpretation of adjusted partial eta squared is actually the same as it is for partial omega squared as well. You can interpret it as the proportion of variance in the dependent variable that is attributable to the independent variable. And so it's a very nice measure of doing that as well. And that's it. So thank you. I hope this is helpful for you. Good luck.